Let me just say a few things about him. I have written down here. So Jayakrishnan did his PhD from Caltech, and this was in 2012. He did postdoc in, I guess, in Caltech itself, and then at CWI in Netherlands with Bert Zwart. And he's been in IIT since 2015. His areas of interest, if I can get this email to open. Just one second. Okay, I can't seem to put his email. His areas of interest are in performance evaluation, in queuing networks, in power networks, in communication networks, and many other areas. What I can say is that in the Indian community, you see few people who are as versatile as Jayakrishnan in his age group in the area of applied probability, and who kind of come up with very creative ideas. So I've always enjoyed being in his talks and seeing the new ideas that he brings and how well he kind of thinks them through and presents them. Thank you, Jay.
वो शायद आसान होगा
Next, we will do the optimization method, particularly as relevant to machine learning. And then tomorrow we'll have Praneet here. Praneet talk about diffusion model. As we so these are tutorials. Along with this, we have industry talks today and tomorrow. And then, as you know, we have online talks tonight. These are high quality talks.
उनको बात करेंगे
From 9 to 10 p.m. today, and then Balaji Prabhakar is going to be from 9 to 10 p.m. tomorrow. The big agenda, because lots of energy, we should have some sugar outside, but should be exciting.
Thank you, Sandeep. I assume I'm audible to everybody? Okay, great. So this is going to be part one of a two-part tutorial on building of confidence intervals in the context of estimation. So I know that the audience is rather diverse. We have undergraduate students, we have graduate students, we have faculty, of course, and I'd like to make this as accessible as possible. So please feel absolutely free to interrupt at any point of time if something is not clear. It is somewhat challenging to cover mathematical material on slides. I'll try, but if anything is unclear in the presentation, please feel free to interrupt. All right. So let me begin with a quick recap targeted primarily at the students of the classical limit theorems in probability, specifically the law of large numbers and the central limit theorem. These are typically results that you would study as part of, say, a first course in probability, right? So the setup is that I have a sequence of IID. IID stands for independent and identically distributed, right? So these are random variables which are mutually independent, and additionally, they share the same distribution, right? So I have such a sequence of random variables. Since they are identically distributed, they have a common mean and a common variance. So throughout, we will denote the mean by mu and the variance by sigma square. Okay. Now, again, this is going to be notation that we will use throughout, and I will give you motivations for this going forward. So bear with the notation. So Sn is going to denote the running sum of these random variables. So Sn being the sum of the first n of these xi. The law of large numbers formally says that if you normalize the running sum by n, in other words, you study the running average of this sequence of random variables, that running average converges with probability 1 or almost surely to the mean, right? So this is the law of large numbers. Intuitively, I mean, this is one, I think, nice way of thinking about it. The law of large numbers is telling us how the running sum scales, right? And it is telling you that the first order behavior of the running sum is a deterministic behavior, which is just n times the mean, right? So if you are, this is just an intuitive way of thinking of the running sum in the context of law of large numbers. What the law of large numbers tells you is that the running sum is scaling linearly with n, with the slope being equal to the mean. And the error associated with this first order approximation, let's call it the law of large numbers approximation, is little o of n. What little o of L means that it is negligible relative to n. If you divide by n, it gets washed away, right? That is one way to think about the law of large numbers. So I mean, just you can draw these pictures quite easily. So I've just simulated these xi's as being exponentially distributed with mean 1. And you see, a bunch of sample paths have been drawn, and the dotted line here is the law of large numbers approximation, right? So you see that the sample paths are kind of fluttering around the deterministic approximation, which is the law of large numbers approximation. And as you take n to be larger and larger, you see that on a relative basis, the error becomes small, right, relative to the first order approximation, which is kind of intuitively what this is suggesting, right? So having seen the first order approximation for the running sum that the law of large numbers provides, a natural next question to ask is, well, what is this error like, right? So what is the spread between the sample paths and this first order approximation? How does that behave, right? The law of large numbers only tells us that this error is sublinear with respect to n. But is it logarithmic in n? Is it random? You expect it to be. Is it some other order? We don't know, right? So this question on what is the error of the law of large numbers approximation like, that is exactly what the central limit theorem answers. Okay. So what the central limit theorem, as a reminder, tells us is that if you actually study on the left hand side, you'll see that the numerator is exactly the error associated with the law of large numbers approximation, right? Equivalently, you can think of it as simply centering the running sum by subtracting away its mean, right? So what the central limit theorem tells you is that this error essentially scales as square root n, right? I should emphasize that implicit in all of this is the assumption that the variance of my random sequence is bounded. If the variance is not bounded, it turns out there's a more nuanced answer to this question, which I won't get into. But let's pretend that the variance is bounded, in which case the central limit theorem tells me that this law of large numbers error, if you will, is actually scaling as square root n. We knew it was sublinear. We know more precisely that it is actually square root n, right? And how does one formalize this? The way you formalize this is to say that if you take the error and normalize it by square root n, right, then this normalized error actually approaches a certain limit in distribution as n becomes large. Specifically, that distribution is the Gaussian distribution, right? So that is what the central limit theorem tells us, right? So again, if I want to think of this from an intuitive standpoint, yeah, this is just a picture. Again, I think a bunch of sample paths taken for n equals 300, and then you actually compute this left-hand side normalized error on each sample path and plot a histogram. You get this very pleasing bell curve, which is actually quite easy to see. Intuitively, what does this mean? It means that if you think of the running sum, the first term here is the law of large numbers approximation. The second term is the second order approximation provided by the central limit theorem. The second term is actually now random. It is square root n times somebody will have to close that, I guess. The second term is actually square root n times sigma, sigma being the square root of the variance, of course, into z. This is my unit variance Gaussian, right? A random variable denoted by that, plus an error which is now little o of square root n, right? This is the one way to think about the central limit theorem, okay? This is just a very quick recap. Now let me get to what is the point of the tutorial itself going to be. Now the idea is that I again have this IID sequence, but this IID sequence is going to be revealed to me sequentially, right? So you can imagine that a sequence of experiments is being performed, the outcome of that experiment being independent and identically distributed. And as I go from time step to time step, one more epoch of the experiment takes place, and then the reading corresponding to that, or the value corresponding to that gets revealed to me, right? And my goal from these sequential experiments, from these sequential revelations, is to actually estimate the mean associated with this IID sequence, right? So the mean is a priori unknown to me. I am performing these experiments sequentially to try and estimate the mean. This is like the simplest possible estimation problem one can formulate. Okay. Now, a natural estimator, you might imagine for this, is simply to take the sample average, right? You got n samples, n outcomes that you've gotten from your n trials of the experiment. You take the average of those. I'm going to call that mu hat n. Right? This is the natural empirical estimator of the mean mu given n samples, right? Independent and identically distributed, right? What the law of large numbers tells us, remember, this is exactly the running average that we were talking about. So the law of large numbers tells us that this sample estimator is going to converge to the true but unknown value almost surely as n goes to infinity, right? So this is also referred to as consistency. So we say that your estimator is consistent, but consistency by itself is a very, very like it's a first order requirement, right? Consistency by itself doesn't tell me anything, right? In a real experiment, having done 10,000 trials, law of large numbers doesn't tell me whether I'm close to my whether my estimate is close to the unknown value or not, right? All I know is that as n goes to infinity, but what does n go to infinity even mean, right? Do I need a million more? Or am I already very, very accurate? That is an information that the law of large numbers does not provide us, right? So therefore, in many applications, these applications might come from hypothesis testing. These applications might come from reinforcement learning, as Sandeep was saying, and so on. In many applications, you actually require, as you go along, computable confidence intervals on the estimation that you have done. Okay. So formally, this is what it means. So after n samples, right, I have my estimate itself, but in addition to my estimate, I want, let's say, a lower bound, let's call it ln, and an upper bound un, right? So the interval spanning from the lower bound to the upper bound is what we will call a confidence interval, right? So I want a computable confidence interval, right, such that formally, with high probability, the true mean, which is unknown and which is what I want to estimate, will lie within this interval with some high probability, right? So this delta is basically some sort of an error threshold or a confidence threshold. If delta is, think of delta as being very small, right? So if delta is 0.1, that means that with 0.9 probability, the unknown number that I seek to estimate lies within the interval. What is the confidence you care about? Do you want to be 90% sure? In that case, you would set delta to be 0.1. If you want to be 99% sure, you would set delta to be 0.01, right? You specify delta, and then in terms of that delta, oftentimes, of course, you want to be able to compute an interval such that the object that I'm actually trying to estimate lies with that confidence within the interval. Okay, so that is what is a confidence interval. So how to construct these confidence intervals is going to be the goal of this tutorial. Okay, any questions on the motivation? It depends. So oftentimes these are tunable in that sometimes, depending on the application, you fix the width and then see, well, what's the probability that it lies. In certain cases, and we'll do a few examples of that, you actually want to fix the confidence. And then, you want to see, okay, what's the width I get because of that confidence, and so on, right? So for example, if you think of the naive, let's say 2 sigma plus minus, that's kind of like saying, I want to fix the probability to be a certain amount and let me see what spread that gives me, right? But one could do it both ways. All right. Yeah, so one more note that I will make along the lines of the question that was just asked, that this confidence may also scale with n, right? maybe as you go along, as you get more and more samples, right, you might want to be more confident of your estimate, right? And so you might want to tune the confidence that you want to associate with your interval with n as well, and that's allowed as well. Okay, fine. So let me begin by an imprecise way of building confidence intervals. Okay, and then we will spend the rest of the tutorial trying to make it correct and more formal. Okay, so the simplest possible and the naivest possible approach for building confidence intervals is to just use the center limit theorem that we defined, that we stated a while back. Right? So what does the center limit theorem tell us? The center limit theorem tells us that if you fix a certain c which is positive, right, then this quantity, which is uh, the difference between the running sum and its mean, what I call the law of large numbers error before, normalized by square root n times sigma, sigma being the standard deviation. The probability that that exceeds c, where c is whatever number you choose, some deterministic constant, that approaches as n tends to infinity to the probability that a standard Gaussian exceeds c. So if I set c to be 1, for example, then the probability that this normalized error exceeds 1 will approach as n tends to infinity the probability that a standard Gaussian random variable exceeds 1. Right? That's the central limit here. Now, if I just massage this out, you will see that if I divide numerator by n, then effectively I get mu hat n minus mu, and then I just multiply the square root n on the other side. And you see that the first statement is in fact equivalent to the second statement. And what is the second statement? The second statement tells me that the probability that the estimate that I'm computing overshoots the mean that I seek to estimate by more than c sigma by square root n. This probability actually approaches a constant, which is the probability that the standard Gaussian crosses the value c. Okay, just a restatement of the center limit theorem, right? Now, I have asked the question in one direction, what is the probability of an overshoot by c sigma by square root n? A symmetric argument just on the left will tell you that the probability that I undershoot by c sigma by square root n, which is to say that my estimate actually goes below mu by more than this amount, also approaches the same limit. Okay, so if I now patch these two together, I will conclude, everything here is formal so far, that the probability that the estimator deviates from the mean on either side by more than c sigma by square root n, that actually converges formally by central limit theorem to 2 times the probability that a standard Gaussian exceeds c. Okay, so this is a formal calculation and it holds for any positive c, right? You can choose c to be any positive number. Okay, so this is just a restatement really of the center limit theorem. How do I use this to come up with imprecise confidence intervals? Let us see. This is just a restatement of the conclusion from the previous slide. Now what I can do is essentially take that right-hand side that I have and specify whatever confidence delta I want. Right? So the probability that the value exceeds, this in absolute, that is upper bounded by, that is approaching this probability, right? So this is basically my violation probability. So I equate that violation probability to delta, whatever delta you might have chosen. Now the advantage I have here is that this right-hand side is computable. I know exactly what the probability of a Gaussian exceeding any threshold is. So if I equate it to delta, I can now invert that and figure out what is the C that will give me that particular delta, right? So if you set delta to be 0.01, then you can figure out what is the C, just a simple numerical inversion to figure out what is the C such that this RHS is 0.01, right? What that means is that approximately the mean, the probability that the estimate will exceed this, will deviate from mu by more than this quantity, which is the inverted C of delta, is going to be at most 1 minus delta, which means to say that with probability, approximately, with probability at least 1 minus delta, the mean will in fact lie in this interval, right? So the probability of a deviation has been approximated by delta, and so therefore with probability at least 1 minus delta, you expect that you will lie within this interval, right? So this becomes a very simple, intuitively constructed confidence interval. Okay. Okay. So you figure out whatever delta you care about, invert this RHS, put it into your favorite numerical program, figure out what C that corresponds to, and plonk that C here, right? And now what this interval looks like is you take your empirical estimator, subtract this quantity. You can think of this as the radius of the confidence interval, C times sigma by square root n. Okay. So either side by that radius, that defines your interval. And now you say that, okay, with probability 1 minus delta, the unknown mu actually lies in this interval, right? And appealingly, the width of this interval shrinks as n grows. It shrinks as 1 by square root n. So the more samples you get, right, this mu hat will, of course, by law of large numbers approach mu, but the width of this interval will also keep shrinking, right? So that is the appealing aspect of this, as you should expect. Okay. So this is our first approximate, somewhat imprecise construction of a confidence interval, right? I say what confidence I seek, and based on the central limit theorem, I approximate a certain interval in which I believe that my estimator lies, that not the estimator, but rather the object, the number I want to estimate lies. Okay. Now, why is this an approximation? Absolutely, right? So we took what was an asymptotic statement as n tends to infinity, kind of pretended that, okay, this holds even for some finite, this equality holds for, a finite choice of n, and plug that in, right? So that is the source of inaccuracy in this. And what we will see throughout, this tutorial is that this can be actually quite inaccurate, right? So this is not the soundest way of doing this. And the source of error is exactly what was mentioned here. We took an asymptotic result and we just applied that approximation blindly for finite n, right? That's the error. Okay, next question. So I said that the distribution from which the xi's are drawn are a priori unknown, right? I don't know the mean, right? So this confidence interval that I've constructed here, is it really reasonable to assume that this is computable by the estimator? I mean, if mu is unknown, it is entirely reasonable that the sigma is unknown as well, right? So it's unreasonable to expect that I know the variance of the distribution, but I don't know the mean, right? So what is is there a counter argument to that? It's absolutely correct to say that it's not reasonable to assume that sigma is known, right? What would a natural, kind of fix to that to make this still half meaningful be? I don't want to get, then I don't want to get into estimating sigma, but what would, much simpler than that. What is sigma hat? Correct, but then I have to worry about the error in the estimation of the sigma hat, right? So then I have to do those things. Like I'm saying simple, quick and dirty fix. Exactly, right? So in saying that this is in fact algorithm computable, I am not really assuming the knowledge of the variance of these xi's. I am assuming a priori knowledge of an upper bound on the variance, right? Which, depending on the physics of the problem or depending on the specifics of the problem, maybe it is reasonable to say that, okay, the variability of this is going to be at most so much, right? So this is a theme that will come up over and over. So you often need some understanding of the family of distributions that you are estimating parameters for, right? So in writing this confidence interval, in spite of the approximation that we get from taking the central limit theorem, which is an asymptotic statement, and plonking that approximation for a finite value exactly, notwithstanding that, the assumption here is that I know some upper bound on the sigma, right? The looser the upper bound, well, the looser your confidence interval is going to be, right? Ideally, you want your confidence interval to be small, right? But if your upper bound is very loose, you will end up having a larger interval than was possible. That's all. Okay? Yes. Indeed. Yeah, yeah. So there are ways of estimating variance as well, but those are even more sophisticated. We'll probably talk about that later. All right. So this hopefully gives you some understanding of what we are trying to do. We want to come up with algorithm computable confidence intervals, right? and we want to do them more formally than what we have done, right? So this is what the tutorial is roughly going to look like. So first we will look at the setting where the random variables are assumed to be from a class of distributions called sub-Gaussians. I'll define formally what sub-Gaussians are, and then we will see how to build confidence intervals for that class. And then we will also see an application of that which comes from sequential hypothesis testing, right? Then we will expand the space of distributions from which these random variables can lie to another broader class called the sub-exponential class, which again also will be defined. And then finally, there is a set that lies even beyond, which is called the heavy-tailed set, right? Where we will see that your naive estimators, right, of just taking the sample average are themselves not the best thing to do, right? And more sophisticated estimators are actually better. Okay, so that's kind of the sequence of okay. All right, so let us start off with the first topic, which is that these xi's are actually sub-Gaussian. So the first order of business is to define what sub-Gaussian random variables are. Okay, so I'm going to just quickly recall what Gaussian random variables are, because sub-Gaussians are related to Gaussian, right? What does it mean to say that a random variable, so this script n you see stands for normal. So when I say x is script n sigma mu square, what I mean is that x is Gaussian with mean mu and variance sigma square. Okay, now this is probably the most familiar definition of a Gaussian that you have come across, which is that the density function is given by this very familiar expression, right? The bell curve, right? But an equivalent way of defining the Gaussian is the following. This is via the moment generating function. So we are looking at the expectation of e raised to s times the centered random variable. So throughout, with if I write mu, what I mean is that mu is expectation of x. Okay, so when you take expectation of e raised to s times a random variable, that is called the moment generating function. It's like an exponential moment of the random variable, right? So specifically, the Gaussian can equivalently be described via its moment generating function. Specifically, the centered moment generating function is given by e raised to s square sigma square by 2. Okay, very simple compact representation in the moment generating space, in the transform space, for those of you who have a kind of signal processing background. Okay, now this is the definition of Gaussians. This is what sub-Gaussians are. Okay, so a random variable is said to be sigma sub-Gaussian. So the convention is that you define it via the sigma parameter. Okay, if and only if the following is true, that the centered moment generating function is upper bounded by e raised to s square sigma square by 2. Right? So immediately you should be able to see the connection between the Gaussian and the sub-Gaussian. In the case of the Gaussian, the centered moment generating function is exactly e raised to s square sigma square by 2. Sub-Gaussian random variables are those whose kind of centered moment generating function is upper bounded by the same quantity. Okay, so this is a sigma. This is a sigma sub-Gaussian random variable. Okay, what we will show in just a bit is that for a sigma sub-Gaussian random variable, the following is true, right? So if x is sigma sub-Gaussian, you center it out, so subtract the mean. The probability that the centered sigma sub-Gaussian random variable exceeds x, where x is some positive number, is upper bounded by this. It's e raised to minus x square by 2 sigma square. Okay, what does this mean? What this means, yes. Sub-Gaussian, so I didn't quite catch your question. Why is it called sub-Gaussian? Or? Not really. It's basically just, I mean, if you ignore the Gaussian definition, this is the definition of sub-Gaussian, right? You take a random variable, you take, subtract its mean out and compute the moment generating function. If that moment generating function is upper bounded by this expression, then it is a sub-Gaussian, right? Why is it called sub-Gaussian? Well, because that right-hand side happens to correspond to the moment generating function of a Gaussian. So the moment generating function is upper bounded by the moment generating function of a Gaussian. So you're right in saying that this class is defined with basically some sort of a boundary built around it, where that boundary is defined using the Gaussian. Right? Very intuitively, and this will come up later as well. What we will see is that we will often talk about the tail of a random variable, the probability that it takes large values. Sub-Gaussian random variables are those whose tail is basically lighter than a Gaussian. So the tail is bounded by a Gaussian. Right? In fact, that is exactly what you will see here. So the probability that this centered sub-Gaussian random variable exceeds the value x, that probability is upper bounded by e raised to minus x square by 2 sigma square. Okay. Now, e raised to minus x means it is decaying exponentially with respect to x. E raised to minus x square means that it's decaying even faster, right? So what that means is that the probability, so the moral of the story here is that a sub-Gaussian random variable is really, really concentrated around its mean. The probability that the value taken by the random variable exceeds its mean by x is actually decaying faster than exponentially with respect to x. It's actually decaying as e raised to minus x square. Right? This is also true of the Gaussian, in fact. So in that sense, the Gaussian is very, very well centered around its mean. Sub-Gaussian random variables are at least as centered around their mean as Gaussian. They are even more centered around their mean than Gaussian. Okay, that is the story here. They are kind of, if you want to think about it in terms of variability, sub-Gaussian random variables are at most as variable as Gaussians, right? They are less variable than Gaussians, right? That is how you should think of sub-Gaussian random variables. Yes. This one. Actually, you don't need a continuity theorem. So continuity theorem comes if you are trying to look at, okay, the moment generating function has a certain limit, and from there you want to conclude something else, right? Here, so I will actually go through the proof of this. The proof is actually just a couple of lines, right? Yeah, so, sorry, say that again. S square, in the definition you mean, e raised to s square sigma square by 2. Sorry. Oh, sorry, that should be s square. This should also be s square. I'm sorry. Yeah, both of these are, yeah, don't know if I. Yeah, sorry about the typo, right? So thanks for catching it. The upper bound is e raised to s square sigma square by 2, not s raised to s as it appears here. Sorry. All right. So you can see hopefully that the tail as indicated by that is decaying faster than exponentially. Now, how do you prove this? The proof is actually very, very straightforward. And the proof actually follows what you might call the Chernoff approach. Those of you who have studied Chernoff inequality from intro probability will see the, So I'm just going to go through this one proof because this idea is going to come up over and over again. Okay. So the idea is as follows. So I want to estimate or bound the probability that the centered random variable, which is sigma sub-Gaussian, exceeds x. Okay. Now I pick some s that is positive. Now, do you see that this probability is the same as if I basically just e raised to s times the left-hand side is greater than e raised to s times the right-hand side? Why? Because for positive s, e raised to xs is actually an increasing function. It's a monotone increasing function, right? So this is exactly the same. Now, why do we do this exponentiation? We do this exponentiation because subsequently I want to apply Markov inequality, right? So the Markov inequality will say that this is upper bounded by the expectation of the random variable on the left, which is non-negative, so that I can apply Markov inequality, divided by e raised to sx. Okay. It is exactly this quantity, the centered moment generating function, on which I have an upper bound by the definition of sigma sub-Gaussianity. Right? So I have an upper bound which is e raised to s square. Yeah, correct here. E raised to s square sigma square by 2. Right? And then in the denominator, I already had an e raised to sx, so I've written it like this. Okay. Now, what is important to note is that the probability that I want to bound is on the left-hand side. I have an upper bound which is parameterized by s. Right? Specifically, inside the exponent is a quadratic with respect to s. But the upper bound holds for all positive choices of s. Right? So therefore, the tightest choice of the upper bound is going to be obtained by minimizing the right-hand side with respect to S. Minimizing quadratics is very straightforward, right? So quadratics that kind of point up, all you're going to do is complete the square and that will do it. So that's all that remains really. So I've just completed the square here. If you don't want to do that, just kind of take the derivative of this, set it to 0, whatever optimal choice of S is, plonk it in, and that will in fact give you the claimed upper bound, right? So it's actually very straightforward. This is what is called the Chernoff approach, where you exponentiate before you apply Markov inequality. That in conjunction with the definition of sub-Gaussianity. Sub-Gaussianity is defined via an upper bound on the centered moment generating function, kind of gives you the tail bound for free. Okay, so what we have proved really is that a sigma sub-Gaussian random variable is very centered around its mean. The probability that it overshoots its mean by more than x, that probability actually decays faster than exponentially, right, as e raised to minus x square. Okay, any questions? All right, so this is just the definition of sub-Gaussianity. I'll state a couple of results which are kind of exercises because I'm going to do something similar later as well. So if you're curious, come back, but these I'm not going to prove. So it turns out that if x is sigma sub-Gaussian, its variance is actually upper bounded by sigma square. Right? So the sigma parameter that parameterizes this class is kind of like an upper bound on the standard deviation of this random variable. Right? Remember we talked about upper bounds on variance in the past as well. Right? These are actually trivial to show, so these are actually exercises for you. If x is sigma sub-Gaussian, then if you multiply x with a scalar, then it actually becomes mod c sigma sub-Gaussian. Now, those of you who have studied Gaussian random variables will recall exactly what happens, an exact parallel to properties with respect to Gaussian. If you multiply a Gaussian with a scalar c, then the variance will scale as c square times sigma square. This is the same as saying that the standard deviation is mod c times sigma. That's exactly how the variance, not variance, but kind of a standard deviation upper bound scales here, right? Similarly, if you add independent sub-Gaussians, you again get a scaling very similar to the scaling that you see with a Gaussian, right? So if I have two Gaussians with variances sigma 1 square and sigma 2 square, if I add those independent Gaussians, you get the sum of the variances, right? That's exactly what happens here as well. So if this is sigma 1 sub-Gaussian, sigma 2 sub-Gaussian, then in some sense the variance upper bound on the sum is going to be sigma 1 square plus sigma 2 square, and so the standard deviation parameter would be the square root of that, right? So the point is that variance of sigma sub-Gaussian scales exactly the way that Gaussian scales. Okay. Okay. So having defined this class, now I have to ask, well, what are examples of sigma sub-Gaussian? Right? What is a trivial example of sigma sub-Gaussian? Gaussian. All Gaussians are sub-Gaussian, right? Any idea examples other than the Gaussian which fall in this class? Yes? T distribution actually is not sub-Gaussian, it turns out. We'll see. Bernoulli, yes, of course. Moments don't, you mean for what kind of moments? Are you talking polynomial moments? Polynomial moments don't vanish. Good, good, good. I understand. So somebody said Bernoulli. Bernoulli is a bounded distribution. You were suggesting a distribution between having support from -1 to 1. So broadly, you might think that because I motivated this class as one where the random variables are very, very centered around their mean, you might think that bounded random variables might fall in, bounded distributions might fall in this category, and that is in fact the case. Okay. And this is actually formalized by what is called Hoeffding's lemma, right? If depending on how we are doing on time, we can go through a proof of this very quickly. What this says is that if a random variable x has support over this bounded interval, let's say from a to b, where a, b is arbitrary, right? Then its centered moment generating function is upper bounded by e raised to s square b minus a the whole square, b minus a being the length of the interval over which the random variable is supported, divided by 8. Okay. So So Hövding's lemma basically gives me an upper bound on the centered moment generating function of any bounded random variable. Okay. From Hövding's lemma, does it follow? Let's ignore the proof of Hövding's lemma for a bit, but does it follow that bounded distributions are in fact sub-Gaussian? The definition of sub-Gaussianity is right above. Yes. And what is the sigma parameter associated with a bounded distribution? The interval length divided by 2, right? Because if you plonk, so bounded random variables with support AB are actually B minus A by 2 sub-Gaussian. Because if you plonk that sigma in, you will see that this upper bound is consistent with the definition of sub-Gaussian, right? So it turns out that all bounded distributions are in fact sub-Gaussian, right? And this lemma is basically telling us what is the sigma parameter, what is the sub-Gaussianity parameter associated with any bounded distribution. It depends only on the interval width, the width over which the random variable is supported. Okay. Okay. Can somebody tell me the time? I just want to get a sense of how we are doing. 50. Okay, fine. So maybe we can go through this somewhat quickly. So this is actually a very easy result to prove. So for such things, I'm going to skim through the proof. The slides will be provided, so you can feel free to take a look at them later, right? Now, remember that the Hövding lemma is basically on the moment generating function of a centered random variable, right? And consistently, all that matters is the width, not the positioning of the interval, but only the width of the interval, right? So without loss of generality, I can kind of translate the interval such that I can force the mean of the random variable to be 0. No loss of generality there. And here, as a starting point, we're just going to use the convexity of the function e raised to sx for positive s. Actually, yeah, this doesn't have to be positive. This is for any s, right? So the idea, I mean, pictorially is actually very straightforward. So the exponential function kind of looks like this. If this is a and this is b, then what you see on the right-hand side is just a straight line joining a and b, and the left-hand side is the exponential function, right? So the convexity actually results in this first statement. Now, this inequality is true for all x lying in the interval AB. I don't think I've mentioned here, but this is true for only x lying between A and B, right? But my random variable also takes values between A and B. So I can replace a little x here by the random variable and now take expectation on both sides. If you take expectation on both sides, I have the moment generating function I care about. Remember, I've assumed the mean is 0, so there's no more centering required, right? So this is the object I want to upper bound in Hövding's lemma, and that's upper bounded by basically this right-hand side. What has happened is that I have expectation of x showing up here, which is assumed to be 0, right? So this is my upper bound. Now the rest of the proof, remarkably, is simply a matter of calculus on top of this deterministic RHS, right? I have a function of s. I have to prove that the RHS function of s is in fact upper bounded by e raised to s square into b minus a the whole square divided by 8. Right? So it's a calculus exercise, if you will. So I'll run through the steps very quickly, but there's nothing deep happening here, the point. So the first thing is to substitute this constant b upon b minus a by x. Okay. If you do that, then you can see that this thing can be written as x as 1 minus x or something of that sort, and that gives you our first rewriting of this right-hand side in terms of x, right? So b upon b minus a is x. Okay. Then I've just pulled out this s raised to a as a common factor that's sitting outside, and everything else is here. So far, it's all just algebra. We're going to make one more substitution. That substitution is going to be, okay, before I do that substitution, I'm actually going to exponentiate this entire thing. So any number is e raised to log of that number, right? So that is what is happening here. And then I see that s times b minus a can also be substituted. I'm going to call it y. So far, all we are doing is basic algebra and substitution. Once I do all of this, then this RHS that I had here can be rewritten as this function. Remember, I have to, my final upper bound is e raised to something, right? So I have to get some exponent sitting outside, which is kind of all we have done. And then just substituted everything else in terms of this x and y. That's all that has happened. Okay. Now you treat whatever is there inside the exponent, treat that as a function of y. Okay. And then you can already check that if you plug y equals 0, then this f of phi is actually 0. Okay. One more level of calculus shows that not only is this function f at 0, it takes a value 0, its derivative also takes a value 0 at 0. This is elementary, calculus on top of this. And with a little bit more work, you can take the second derivative of this. It has a very clean form. And it turns out that that second derivative is upper bounded by a quarter, no matter what the value. Okay. So a consequence of all of these, the fact that the first derivative at 0 is 0, the function value at 0 is 0, but the second derivative is universally upper bounded by a quarter, means that by Taylor's theorem, the function itself is actually upper bounded by y square by 8. That's my second order, term from Taylor expansion. And that's it. That completes the proof, right? So it's basically just, you take convexity of the exponential function to begin with. And after that is just some algebra manipulation, elementary calculus. Finally express it as a function of y. And then we bound that function universally using Taylor's theorem. Because that function very conveniently has, first derivative 0, second derivative, value 0, first derivative 0, and the second derivative is bounded. Right? So the Taylor expansion around 0 gives you this function. Okay. So this is just a proof of Hovding's lemma. What that establishes is that all bounded distributions are in fact sub-Gaussian, and they are sub-Gaussian with a sigma parameter simply of half of the interval over which the distribution is supported. Okay. Now, how do we finally go about constructing confidence intervals for this setting? Okay, so we are back to our setting where I have an IID sequence revealed sequentially. Now it is also assumed that the random variables in the sequence are sigma sub-Gaussian. Now I want to once again emphasize, in assuming that the sequence is sigma sub-Gaussian, you are assuming two things. You are assuming intuitively, of course, that the random variables that you are actually seeing are highly concentrated around their mean. Right? And in assuming that they are sigma sub-Gaussian, you are assuming that you know an upper bound on the standard deviation or equivalently an upper bound on the variance. Right? We are not getting rid of that. We still need the upper bound, but we are just being more formal with respect to the construction of the confidence interval, as we will see. Okay. Now, I told you how the sigma parameter scales with adding up, scales exactly like Gaussians, right? So if I think in terms of variance, if I sum n independent random variables, the variance becomes n times sigma square. The parameter becomes square root times n, square root n times sigma. Now, if you multiply a number by a Gaussian by a scalar, then the variance gets scaled by basically the absolute value of that number. So when I divide this running sum by n to get my estimator, I get a sigma by square root n sub-Gaussian. Okay. And it turns out this itself is enough for me to construct a confidence interval, right? Because when I'm taking the running average of a sequence of sigma sub-Gaussian random variables, the estimators that I'm collecting along the way are in fact sigma by square root n sub-Gaussian. That implies a certain concentration of these estimators around their mean. And the mean of the estimator is exactly the object I'm trying to estimate. Okay. So this is the conclusion from the previous slide. This is exactly the inequality that we proved before using the Chernoff approach. The probability that this quantity mu hat n exceeds its mean value, which is the mu that I want to estimate, by more than c, is upper bounded by this. It's just e raised to minus c square divided by 2 sigma square. And the sigma has been substituted to whatever it is. Okay. So this is basically giving me an upper bound on the probability that my estimator is going to overshoot the true value by more than c, where c could be any positive number of your choice. Okay. Now, just as you did the Markov inequality on the right, you can also do the Markov inequality and the exponentiation on the left. So the exact same calculation that we have done before also implies the probability of an undershoot by c is also upper bounded by exactly the same quantity. Okay, so if you patch these two together, you see that the probability that you have a deviation of more than c between the estimator and the true value. In other words, the probability that your estimation error exceeds in absolute value c is upper bounded by 2 times this quantity. This is true for any finite n. This upper bound holds for any finite n. This is not an asymptotic result like the central limit theorem was. Now I can invert this to get an algorithm computable or estimator computable confidence interval, right? Yeah, so moral of the story, and this is something that I will contrast subsequently when we study, kind of more variable distributions. Note that the probability that you have an order 1 error in the estimator, order 1, I mean relative to n, right? So C is order 1. So the probability that you have an order 1 estimation error is actually decaying exponentially with the number of samples, right? That's an appealing property, as you can imagine, right? Now, how do I construct a confidence interval? Well, you decide what is the probability of error that you're willing to tolerate. What is the probability that the value that you care about actually lies outside your confidence interval? You fix that to be delta, whatever that might be. And now just invert this and figure out what is the C corresponding to this, right? In this case, this is a trivial calculation. You can invert this and the C will end up being this, right? So just equate this right-hand side to delta and figure out what C evaluates to. That now becomes the radius of your confidence interval, right? So now formally we can say that if you fix your delta, which is whatever confidence you care about, then if you construct a confidence interval which is centered around my estimator and has a radius which is equal to square root of 2 sigma square log 2 by delta divided by n, with probability at least 1 minus delta, the true but unknown value will lie within this interval, right? And this is true for any n. So there's no asymptotic approximation. This is a formally sound confidence interval construction. Okay. Some basic sanity checks you can make. If you fix delta, right? So delta is 0.01, so which means I want a 99% guarantee that mu lies within the interval that I'm computing. This width for that fixed delta will actually shrink as you get more and more samples, and it shrinks by 1 by square root n, right? Also, intuitively, you should expect that as your delta becomes smaller, which means that you want to be more and more sure about having caught the correct value of mu within the interval. If you shrink delta, the width of the interval will grow, right? If you want more surety, then your interval has to expand clearly, okay? And one more thing I did not point out, but should actually be apparent, is that this delta is something I can choose. So in particular, there's nothing that stops me from setting delta in a manner that also depends with n, right? So we will see examples of this where there might be applications where I want the confidence associated with the interval to also scale with n, nothing changes, right? If instead of delta, you replace that by delta sub n, right? Everything that we have constructed continues to hold. Okay. So this is how you construct confidence intervals for the sub-Gaussian setting. Okay. This is just easy. I'm just stating it for completeness. If I specialize this to bounded random variables over the interval a to b, then remember these are sub-Gaussian with sigma being just b minus a by 2. So I can just apply blindly. So this is the concentration inequality that you would get for the probability of a C deviation or a C error between the estimator and the mean, right? That scales in this manner. All I've done is substituted sigma equals b minus a by 2 in the preceding inequality, right? This inequality is called Hoeffding's inequality. Okay. And finally, for bounded random variables, this now becomes an explicit statement of the confidence interval, right? So again, it simply boils down to a substitution of sigma equals b minus a by 2 in the previous construction, right? So we have seen that even if you want to specialize to bounded random variables, this is how you can do algorithm computable or estimator computable confidence intervals, right? In the bounded setting, it is more reasonable to assume that you know the bound, right? So if you're collecting customer ratings from Amazon or something of that sort, you know that customer ratings are going to be between 1 and 2, right? Or sorry, 1 and 5 or 0 and 5 or something of that sort. It turns out that knowing that interval automatically gives you an upper bound on the variance that is possible, right? And that's how your sigma is constructed. Your sigma is basically telling you what is the worst case standard deviation associated with a random variable over that distribution, right? So therefore, If I know the interval over which my random variables are supported, implicitly I know an upper bound on the standard deviation, and so therefore I know my sigma to plonk into my confidence interval. Okay. All right. Now let us apply this to a hypothesis testing problem. Okay. So the idea is actually very straightforward. I give you a coin. Okay. I am going to tell you ahead of time that the coin is biased. Okay. It's not a fair coin, right? Your goal, so I'm given a biased coin. The probability of heads is not half. It's an unfair coin, if you will, right? Your goal via repeatedly tossing this coin, right? Feel free to toss it. Your goal is to figure out whether this is a coin that favors heads or favors tails, right? So this is an experiment that maybe Amitabh Bachchan got this coin from somebody else, and he had to do this experiment before figuring out how to rig the toss, right? Between his friends. So that's the hypothesis testing problem we are after, right? I'm giving you a biased coin. Your job is to determine the direction of the bias, right? And to do so with a fixed confidence, right? So I give you this coin in your hand, and I tell you that you are supposed to report to me whether the coin is heads heavy or tails heavy, right? With probability at least 1 minus delta. In other words, if I specify delta to be 0.1, your answer should be correct with probability at least 0.9. So I'm imposing a probabilistic accuracy guarantee on you ahead of time. What I'm not imposing is how many times you toss the coin. You toss it as many times as you want. But in the end, your answer should be correct with probability at least 1 minus delta. Problem setting clear? So we want to use the machinery that we have built earlier to come up with a sound confidence interval based approach to solve this hypothesis testing problem. Any questions on the formulation that we are studying? The simplest possible, hypothesis testing problem to construct. Okay, but it's a fixed confidence problem, right? Your answer should be correct with probability at least 1 minus delta, where delta is pre-specified to you. Okay. All right. So natural thing to do would be to map heads to 1 and tails to 0, right? In which case, every time you're tossing the coin, you're basically getting a sample from a Bernoulli distribution with parameter p, because p is the probability of heads. Okay. So what are we really saying? What we are saying is that your job is to figure out, when you say, is it heads heavy or tails heavy? You want to figure out whether the bias or the mean of this Bernoulli random variable, is it more than half or less than half? Okay. What do I do? The natural thing to do would be to just estimate the bias of this with samples, right? So after t samples, you have tossed the coin t times, and you got a certain number of heads and a certain number of tails, or equivalently, a certain number of ones and a certain number of zeros. What is a natural estimator for the mean value or the p value associated with the Bernoulli? It is just going to be the frequency of heads, total number of heads up to time t divided by the total number of tosses up to time t. The denominator is just t. Okay. This is the natural estimator that you might think of. This is in fact the empirical estimator associated with the Bernoulli. Okay. Now what we know from our machinery is that Bernoulli distributions are bounded between 0 and 1. So they are bounded. Being bounded, I know how to construct confidence intervals, right? So which means that I can choose what delta t is. Okay. But whatever I choose delta t to be, the actual bias p will lie between plus minus an interval which is p hat minus something, p hat plus something, and that radius is in fact given by square root of 2 by delta t divided by 2t. All we have done is applied b minus a equals 1 in the preceding inequality. Okay. So I know after t tosses that, okay, this is where my empirical average is pointing. I know that with a confidence that I can dictate delta t, I can compute an interval around this estimate and say that, okay, with that probability, the true p is actually going to lie in this interval. Okay. Now, any thoughts on how I should go about setting delta t and how I should go about solving the problem in such a way that finally, when I do give my answer, my answer should be correct with probability at least 1 minus delta. Any thoughts on what you might do? I mean, the trick is, of course, to use these confidence intervals in some manner, right? Uh, so eventually, you kind of want to move this interval to either side of half, right? So if the interval is kind of on the right side of half, you might think that, oh, with high probability, assuming you have tuned the intervals correctly, with high probability, this is a heads-heavy coin, right? If the interval shifts, so what does it mean to say that the interval shifts to the right of 0.5? Which means the left end point should be to the right of 0.5. Or if the interval shifts to the left of 0.5, then you might say with some confidence that, oh, this is a tails-heavy coin. Okay. Now the question is that you don't know when that's going to happen, right? Because you don't know how long it is actually going to take for the interval to actually go to either side of half, right? So I have to set delta t in some suitable manner. So here is a very simple, naive way of setting this delta t in a, in a correct manner, in that your answer will be correct with probability 1 minus delta. Okay. So I'm going to set delta t to be delta. Remember, delta is my overall error probability, right? Which has been pre-specified to me. I'm going to set delta t to be delta divided by 2t square. Okay. T runs from 1, 2, 3, 4, and so on, right? With that choice of delta t, I keep track of these confidence intervals as I go along. Now, why have I chosen delta t to be delta by 2t square? So what is the probability that the confidence intervals ever become invalid? At any time t, when I say confidence interval becomes invalid, what I really mean is that the mean is actually outside the confidence interval, right? At time t, the probability that that happens is at most delta t. What is the probability that it ever happens? The probability that it ever happens is the union of it happening at time t. So by the union bound, the probability that my confidence intervals ever become invalid, assuming that I'm doing, an infinite sequence of coin tosses, is in fact upper bounded by summation of delta t. Yes? That is overkill, right? Yeah, yeah. So let's finish the construction and you will see this is not the only way to do it. There are many ways of doing it. Yeah, yeah. So the probability that the confidence intervals ever become invalid is at most summation of delta t. Now you can see why delta t has been chosen in this manner, because 1 by t square is summable, right? And in fact, summation of 1 by t square, you guys should know the answer better than me. It turns out that it is at most 2. So that will cancel out. And so the sum is actually at most delta. Pi square by 6 or something, right? Yeah. So the point is that having chosen delta t in this manner, the probability, with probability at least 1 minus delta, the confidence intervals are always valid. So I don't know how long my experiment is going to run, but through the entire run, even if I make infinitely many tosses, my confidence intervals are always going to contain the true and unknown bias P. Okay, this is the crucial part, right? So that's what is being written here. The confidence intervals remain valid or correct at all times with probability at least 1 minus delta, right? So this is what I will refer to as the good event. I have constructed my delta t in such a way that the good event has probability at least 1 minus delta. What is the good event? Through the entire run of my experiment, the unknown p will always lie within the interval that I'm computing. Which means on this good event, if the interval ever went to the right of 0.5, I can quit and say the coin is heads heavy. If the interval ever shifted to the left of 0.5, I can quit and say that the coin is tails heavy. Right? Because on that good event, the true value will lie in the interval. So if the interval itself is to the left or right of 0.5, true value will also suitably lie in the left and right. Okay. So what is the algorithm now? Set delta t in this manner and keep tossing. keep tossing away till the interval shrinks either to the left or right of 0.5. If it goes to the right, then stop at that point and say that the answer is heads. If it goes to the left, stop and say that the answer is tails, right? This is not the most efficient way of doing things. There are other more sophisticated ways of doing this. But this is just a simple application of where I can use confidence intervals to, in a sound manner, to prove a sequential hypothesis testing problem. Okay. Any questions on the correctness of this approach? By correctness, I mean that this approach should provably give you the correct answer with probability at least 1 minus delta. The probability that you make a mistake is at most delta. Okay. All right. Okay. Now here is a quick exercise for the students in the room. So remember, I told you that there is a good event. The good event is that the confidence intervals remain valid at all times, and that good event has probability at least 1 minus delta. So on the good event, on which you're also guaranteed to give the correct answer, come up with an upper bound on the number of samples I need. If you think about it, even though the centering of this p hat, p hat itself can move around over time, the width of the interval is actually going to be shrinking deterministically with t, right? Because it's just, well, plug in whatever delta t you have out here, and you will see that something is actually shrinking deterministically with t. That, combined with the fact that the interval always has to contain the true p, will tell you that at least in so many pulls, the interval should have either gone to the left or to the right, depending on the correct value. You should be able to come up with a precise deterministic upper bound on the number of samples or tosses required in the good event. Okay, that's an exercise for you. Now let us go beyond sub-Gaussian. Somebody give me a time check, please. 15 more. Okay. So you can imagine that the class of sub-Gaussians that we have been working with all this while is actually rather limited, right? So these are distributions that are extremely centered around their mean. And you will be hard-pressed to find examples of sub-Gaussians outside bounded distributions or outright Gaussians themselves. Okay. So it's a very restricted class to work with. And you might want to actually work with a broader class of distributions because they might arise in practice, right? A simple exercise for you is to check that the exponential distribution is in fact not sub-Gaussian, right? It's trivial in fact, because the exponential tail, as the name suggests, decays exponentially. The probability that an exponential distribution takes a value greater than t is exactly e raised to minus nu times t, right? So which means the tail is actually decaying exponentially, but to be sub-Gaussian, the tail has to decay faster than exponentially. So that itself tells you that exponentials are in fact not sub-Gaussian, right? If you take a Gaussian, which is sub-Gaussian, and if you square it, again, you will not get a sub-Gaussian anymore, right? Because a Gaussian by itself has a tail that decays as e raised to minus x squared, but once you square it, the tail has a different decay. In fact, the tail decays exponentially, and so therefore even that is not sub-Gaussian. So you can do small things to sub-Gaussians and go out of this class because it's a very restricted class. Okay, that motivates for where we want to go next, right? So this next class of distributions that we will consider are in some sense a class of distributions that allow for more variability than the sub-Gaussians. Sub-Gaussians are extremely centered around their mean, right? So if you want to allow for more variability, the next class that we will consider is the class of sub-Exponential. Okay, now sub-Exponential distributions, this is a reminder of the definition of sub-Gaussian first. Sub-Gaussian random variables are defined via an upper bound on the centered moment generating function, right? So the upper bound, this is still typo, e raised to s square sigma square by 2. Okay. A random variable is going to be sub-exponential, but now with two parameters, lambda and alpha. Okay, this is messed up. Yeah, again, wherever you see s raised to s, you should treat that as s squared. So the centered moment generating function is in fact upper bounded by e raised to s square lambda square by 2, lambda being the first of the two parameters defining this class. So it structurally looks like it's very similar to the upper bound that we assumed on the sub-Gaussian setting, right? If you replace lambda by sigma, it looks exactly the same. But the key difference is that while in the sub-Gaussian case, you assume that the upper bound held for all S. Again, the typo. This should have been for mod S less than 1 by alpha, right? So there you expect that upper bound to hold for all choices of S. In the sub-exponential case, the upper bound only holds for mod S less than equal to 1 minus alpha. So alpha being the second of those two parameters, right? So the first parameter in the, just a moment, the first parameter in the sub-exponential case is basically giving you an upper bound on the centered moment generating function, analogous to how we had in the sub-Gaussian case. The second parameter is telling you what is the interval around the origin on S on which this inequality is actually expected to hold. In particular, we are not imposing that the inequality hold for all S. Yes. No, in both cases, this in the sub-Gaussian case, this S could take any real number. Here, yeah, this is a typo. Sorry, this should be mod S less than 1 by alpha. So S can take any value between minus 1 by alpha and plus 1 by alpha. So we are allowing positive, negative in both cases. Here, we are only expecting this bound to hold over an interval around the origin. There, we expected the bound to hold for all S. Is the definition clear? Yeah, I'll fix the typo before the next time we meet so I can remind you the correct value. Yeah. So from here, I hope from the definition it's already clear that sub-Gaussians are a subset of sub-exponential, right? I can take alpha to be arbitrarily small and, right? So we are expecting the same upper bound to wholly hold over a certain interval around the origin, right? So it's clear that sub-exponentials expand on the class of sub-Gaussian. This class of sub-exponential distributions is also referred to as light-tailed distributions, right? To be contrasted with heavy-tailed distributions, which we will cover later. Okay. Yes, typo remains. No, this is the definition of light-tailed distribution. So to be more precise, this is the definition of a sub-exponential with parameter lambda alpha. A random variable will just be sub-exponential if there exists a lambda alpha such that this holds. So this class here is the space of all such distributions, and that class is also called light-tailed. Okay. Okay. Definition with the typo. This is the lemma that basically tells you about what this class actually includes. Okay. So it gives you different equivalent definitions of sub-exponential. Now, so the lemma says that these three statements are in fact equivalent. The first of these statements is that x is sub-exponential. As was asked just now, when I say x is sub-exponential, what I mean is there exists a lambda and alpha such that that definition holds. Okay. The second is that there exists some C naught greater than 0 such that the moment generating function is in fact bounded for mod S less than C naught. Right? So the first definition seems to be stricter because I'm saying that in a neighborhood around the origin, I'm giving you a very explicit upper bound on the moment generating function, on the centered moment generating function. The second one looks like it's weaker, but it's actually equivalent. All we are saying is that the moment generating function is bounded in an interval around the origin. Yeah, there is some positive C naught such that between minus C naught and C naught, some interval around the origin, the moment generating function is bounded. That's it. Okay. And the third says that there exists some positive constant C1 and C2 such that the probability that the absolute value of the random variable exceeds X, right? So this is basically the right and the left tail combined. That probability decays exponentially. So C1 is a constant prefactor sitting here, C2 is in the exponent, right? So we have now three equivalent definitions of sub-exponential. The first was in terms of the explicit upper bound on the centered moment generating function from the definition on top. The second says that the moment generating function is finite in some neighborhood of the origin. The third says that the tail decays exponentially. This is like a two-sided tail. Okay. And already you can see the expansion in the space. Earlier we had a tail that was decaying as e raised to minus x square. Now my tail is decaying as, and mind you, these are not implications, these are equivalent statements. Right? So any distribution with a tail, one-sided or otherwise, which decays exponentially is in fact in this class. Okay. All right. So let us see why these statements are in fact equivalent, right? Because you might think that the definition that we wrote here first was actually more restrictive than the subsequent equivalent, right? So that 1 implies 2 is trivial because the definition itself said that there is an explicit upper bound on the centered moment generating function. So obviously then the moment generating function must be bounded over that interval, right? So 1 implies 2 trivially. To see that 2 implies 1, what we will use is basically a Taylor expansion of the moment generating function around the origin, right? Those of you who have studied moment generating functions in intro probability will know that the reason this function is called the moment generating function is exactly because if you take the Taylor expansion of that around the origin, you get all the moments showing up as coefficients, right? So if you see the fact, if I assume that 2 holds, then the moment generating function exists or is finite in some neighborhood around the origin, which means I can do a Taylor expansion of that around the origin. Okay. Now, so if I just center that out, what the Taylor expansion will do is that at the origin, the value is just 1. The leading coefficient will have the coefficient being the mean, but because I've centered the random variable, that term is now washed out. And finally, the S square coefficient is going to be the variance, right? So in a neighborhood around the origin, you can write the moment generating function as up to second order terms plus little o of S square. You will have lower order terms subsequently. Right? This comes from the Taylor expansion of the moment generating function, which has been assumed to be finite in the neighborhood of the origin, right? But what the definition tells, so the RHS that we wanted, right? The upper bound that we wanted is of the form e raised to S square lambda square by 2. What is the Taylor expansion of this in the neighborhood of the origin? It's 1 plus, well, it's just a Taylor expansion of e raised to x plus S square lambda square by 2 plus again little o of S square, right? So if I up to second order, this is what the moment generating function behaves like, and this is what the exponential function behaves like, right? So to make this inequalities be satisfied in some small interval around the origin, all I have to do is choose lambda to be greater than the variance, right? So basically the moral of the story is that the fact that the moment generating function exists in a neighborhood around the origin implies and is equivalent to having an upper bound of the form e raised to S square lambda square by 2 in a neighborhood of the origin. It comes for free. Okay. So that basically tells you that 1 and 2 are in fact equivalent. Okay. To look at 2 implies 3, we are assuming that the moment generating function is finite in some neighborhood of the origin. Whenever you see this, the way you would prove, let's say, a tail bound would be via, again, a Chernoff type approach, you would expect, right? So pick, because I have an interval, pick some S0 over at which the moment generating function is in fact finite, S0 being positive. I can always do this so long as 2 holds, right? Then the probability of a positive deviation, x greater than x, again I exponentiate on both sides by e raised to S0, right? And then I apply Markov inequality, right? The point of this is that this exponential function, this term is just a constant, right? I have a constant multiplied by e raised to minus S0 x. So if I see this RHS as a function of x, I have a constant times something that is exponentially decaying with respect to x. The same thing can be applied on the left, right? So you can do the same exponentiation, but now applied on the left, and you will get a similar bound. So this tells you that there is a C1 and C2 that satisfies 3. Okay. So this basically very easily shows via just a Markov inequality Chernoff approach that 2 implies 3. That 3 implies 2 actually also follows quite straightforwardly, right? So the way you show that 3 implies 2, under 3, remember, I have a tail bound of this kind, right? I have to prove from there that exponential moments are finite. Now, let's pick a positive s and then prove that for a small enough s, this exponential moment is finite, right? Now, e raised to sx is a non-negative random variable, right? So for any non-negative random variable, its expectation can be written as an integral of its tail. The probability that that random variable takes a value greater than x, the CCDF, the complementary cumulative distribution function, if you will, the integral of the CCDF from 0 to infinity is the expectation, exactly, right? So this is another way of writing this. The reason we are writing this is because somehow I want to use this bound, right, to show that this integral converges. So now all we do is massage. E raised to sx greater than x is the same as saying that x is greater than log x by s. But I now have an upper bound on the probability that x takes large values. So I plug that in. When I plug that in, I get something that looks like e raised to minus c2 times log x by s, which is basically just x raised to minus c2 by s, right? So all that I can see is, remember, c2 is assumed to be some positive value, right? If I choose s small enough, then that power law decays fast enough so that this integral will converge, right? So for example, I can simply choose s to be c2 by 2, in which case I'm looking at integral of x raised to minus 2, right? All right. So that shows that in fact the positive exponential moment is finite. You can do the same thing on the other side. So this basically gives you a full characterization of sub-exponential or light-tailed distribution. Finiteness of the moment generating function in a neighborhood of the origin, right? Which also implies that the tail actually decays exponentially. Okay, and this represents a much broader class as compared to the sub-exponential, sub-Gaussian class that we studied earlier. Okay, now the construction of confidence intervals can be done very quickly. So the fact that I have this definition of sigma sub-Gaussian, sigma sub-exponentials with parameter lambda and alpha implies that the tail actually decays in this manner. Okay, I'm not going to go through the proof of this. The proof is identical to what we did before. I do exponentiation, Chernoff, and the definition gives me an upper bound on the moment generating function. I plonk that in and optimize with respect to the exponent. That gives me this, right? The moral of the story here is that the probability that the centered sub-exponential random variable exceeds x, if x is small, then you can upper bound very similar to the sub-Gaussian case. Right? For small exceedances, you get a bound that looks like the sub-Gaussian bound. But for large x, you actually get something that is exponentially decaying and not super exponentially decaying as before, right? And that is consistent with the lemma that we proved before. Okay. So this is how, and you can prove a symmetric inequality on the left. So this is a probability that you have a positive overshoot by x. Similarly, negative overshoot by x will have the same bound. Okay. So the tail basically asymptotically decays exponentially as it should, because that's what we proved earlier, right? So now to derive confidence intervals for the sub-exponential case actually comes for free using exactly the same aggregation properties that we did before. Okay. So if I have IID sub-exponential random variables with parameters lambda and alpha, if you add all of them up, again, moment generating functions behave very cleanly with respect to sums and scalar multiplication. So it's a straightforward exercise for you to check that in fact the empirical average is going to be sub-exponential with these parameters. So remember, lambda is an upper bound on the variance. So it's not surprising that it scales exactly the same way as it did as the previous case. It turns out that this alpha actually scales by 1 by n. Okay. So once I know that mu hat behaves like this, using this inequality that actually holds for any sub-exponential random variable, it becomes trivial to derive a concentration inequality for mu hat n, which you then invert to construct a confidence interval exactly as before. Okay, so we have worked with an expanded class of distributions, which now have exponential tails rather than e raised to minus x squared time tails. But essentially, we are able to similarly construct algorithm computable confidence intervals for mean estimation. Okay. Right. So this is a summary of where we are at this point. So we have sub-exponential or light-tailed distributions on this left. Sub-Gaussians are a subclass. I mean, I don't know too many examples except for the Gaussians, of course, and bounded distributions. But you have other examples here. The exponential, the gamma, the hyper-exponential, any number of such distributions will lie here. Those of you who have studied the class of phase-type distributions, I will not define them here, but this is a broad class of distributions that cover convolutions, mixtures, mixtures of convolutions, convolutions of mixtures, and so on of Gaussian distributions. A very rich class of distributions. They are all actually going to be light-tailed. Okay, so this is all that we have on what we have seen so far, right? So what we will do in the next remainder of this tutorial is to basically explore what happens here, right? What we will see is that heavy-tailed distributions, which as the name suggests are distributions which are in fact not light-tailed, These distributions behave fundamentally differently as compared to light-tailed distributions, right? In particular, we will see that outliers play a very important role when you're dealing with data from heavy-tailed distributions. And so just a naive empirical average doesn't necessarily work really well. Ideally, you want to do more robust things than that, right? So we will discuss constructions of confidence intervals with heavy-tailed random variables in the second half of this tutorial. Any questions on what we have covered so far? If you tell me which part, I can go quickly. Okay. Are you? Yeah, I've been a bit imprecise. I don't really, yeah. See, remember, it's a probability that I'm integrating. So I don't really care about the behavior of this around origin. Is that what is bothering you? I mean, you can just take that to be 1 if you want. It's the behavior at infinity that I really care about bounding. Okay, so we'll stop here and let's move on to the next session.